Hey guys, welcome back. So this is going to be the second part of the titration. I'll go through the agenda of what we're going to talk about in all of this. First, we're going to talk about the acid-base properties of salts. So looking back at conjugate acids and conjugate bases, we want to be able to identify those so that we can know what they might do in solution. So we need to be able to predict the acid-base properties of salts. We're going to do that. We'll talk about homogeneous versus heterogeneous solution equilibria. And then we'll talk about acid-base titrations and indicators. So titration is what we're going to be talking about. And this goes with experiment 3, which we're going to be doing in the lab soon. So there we go. Let's go ahead and get to our next slide. So the first thing we want to talk about are the types of salts that we need to be worried about. So when I have a salt and I dissolve that, I have it's usually a metal and an anion that goes into solution. So it's an ionic compound, almost always made from a metal and an anion of some sort. Polyatomic, could be nonmetal, could be any number of things. And we end up with a metal that has a positive charge of some sort and an anion that has a negative charge of some sort. And so we get dissolution of that material and dissociation of that material. So it comes apart. After it comes apart, then it depends on what it is, what might happen, all right? Normally, when we have alkali metals and alkaline earth metals and the conjugate base of a strong acid, then nothing happens, okay? So when we talk about like sodium chloride or ammonium fluoride, or no, not fluoride, ammonium bromide, things like that. That's something that we don't have to worry about so much. So alkali metals, alkaline earth metals, and then anything that is the conjugate of a strong species is not going to be something we have to worry about. So those are our neutral compounds. Those won't do anything with our solutions. But what happens when we have a solution that goes in when we've had a strong acid like HCl and it reacts with a weak base? So let us consider for the moment HCl plus NH3, which is a weak base. That's going to give us an NH4Cl, right? And when we have that thing come apart, we end up with the NH4 plus and the Cl minus. Now the Cl minus really is not going to react with H2O, and so we're not going to end up with any sort of thing that happens with that. But an NH4 plus, we can get with an H2O, and we're going to end up with H3O plus and that NH3 coming back. And that's because it's a weak base. So when that happens, when we have the conjugate of a weak base going into solution, that tends to lower our pH. So higher concentration of H3O plus, and then lower pH, okay? So lower pH due to higher concentration. The opposite is true when we have a strong base and a weak acid. So when we talk about NaOH plus HF, that'll give me an NaF and an H2O. And it's that NaF that we're worried about. So that Na, it's not a positive, sorry, that's an F minus. That Na, being an alkali metal, is not going to do anything in water. So that's not something I need to worry about. But that F minus, it does. So we take that F minus, we add H2O to it, and we end up with an H3O plus. No, we don't. Sorry, it takes it off of there. So we end up with an HF plus an OH minus. Sorry, I apologize. And that OH minus, therefore, is going to raise the pH because the concentration of the OH minus is going to get bigger. Okay, so that's what we have there. So we need to be able to identify when we have the conjugate of a weak acid or a weak base that's then going to be able to give us that weak acid or weak base back. That's what we're looking at. All right, so things with fluorine on them, things with ammonium, NH4 plus, some of the, acetate is another one. Any of the ions that come from these weak acids. So that's something that you can look for. And again, we have some weak acids and weak bases that are listed on page 10 in the lab or in the exam handouts. And those can give you the anions that go with each of those weak acids and weak bases. Okay. So that's what we need to talk about in terms of salts, because they have an effect on pH. So when we talk about the properties of those salts, we can see from the table that we have, and I'm going to zoom in so you can see that, because I know it's really hard to see unless we do. If the cation from a strong base and the anion from a strong acid, then it's not going to have any effect. Our pH will be 7. If we have a cation from a strong base and an anion from a weak acid, right, when we do that, that means we're going to form that OH minus just like we did with the HF reaction. Okay, so like when we have anion from a weak acid, that F minus plus an H2O gives us that OH minus plus HF, and of course that raises our pH. When we have the cation from a weak base and the anion from a strong acid, so something like NH4Cl, it's the NH4 plus that we're concerned about. That gives me H3O plus an NH3. And that's going to lower our pH because we've formed that H3O plus. Okay, higher concentration of H3O plus, lower pH. When we have the cation from a weak base and the anion from a weak acid, then it depends. Okay, we have reactions that are going to happen because of both the anion and the cation. And so it depends on the size of Ka versus Kb, what we're going to end up with in terms of pH. So I'm not going to ask you to predict that. Okay, that is not something that we're going to be talking about. When we have small, highly charged cations and anions from strong acids, okay, then that gives us a hydrated cation, right? So we can get that to react with water. And when that happens, our pH goes down. And we'll talk about that when we get into the precipitation. So we aren't going to worry about it too much here, but that's how that happens, okay? So I want you to be able to predict, would our pH go up, go down, or stay the same based on the nature of a salt? So if we were to talk about NaF, again, that F minus is going to be a problem because it'll react with the H2O to give me HF back plus OH minus. So that's a problem. The NH4 from NH4I is also going to be a problem because that's going to give me NH3 back and an H3O plus. When we talk about KCOOH, right, that HCOO minus plus H2O, this is the conjugate base of the weak acid. So we end up with our formic acid, HCOOH, plus an OH minus. And an RBBr isn't going to do anything because an RB is an alkali metal. The Br is the conjugate of a strong acid, so we wouldn't have to worry about that, okay? So we need to make sure that we're looking at what we have, right? Now, how do I know that the Na wasn't a problem? How do I know that the I wasn't a problem? How do I know that the K wasn't a problem? Na and K are both alkali metals, and so I wouldn't expect them to be a concern. The I that we had is, the conjugate of a strong acid, so I'm not concerned there. Okay, so that's how I know that. Do I know all of them every time? No, I don't. It's just not something that I deal with that often, so it's not something that's readily known to me. Okay, questions, comments, problems on that? I hope not. I'm going to zoom back out so that we can see the whole thing. If you have questions about that, please let me know. That's going to end our discussion of the acid-base properties of salts. So I'm going to stop this video, get another one set up, and then we'll start talking about our next topic. Thanks, guys. Talk to you soon.